Welcome to our video series. We will love to hear your ideas for future videos. Now, let's dive into the topic of the biological blueprint. In this page, we will cover the fundamental breakdown of how we currently design computers versus how the human brain actually computes. For 70 years, we have been polishing what some call a prison cell of rigid architecture. We are looking at standard CPU layouts with logic gates and memory buses that feel increasingly outdated in the face of complex intelligence requirements. On the right, we see the future, a neural core built on a morphing boundary. This includes the dendritic tree, the axonal pathway, and the synaptic junction. These elements allow for parallel distributed processing and analog weights that offer incredible plasticity. By understanding this teardown, we can begin to see how physical AI seeks to replicate the self-organizing complexity of biological life. We are shifting from a world of fixed paths to one of fluid growth, where the hardware itself begins to mirror the wetware of our own minds. This transition is not just about speed, it is about the very nature of how information flows through a system. As we move away from traditional logic gates and memory architectures, we embrace a model that is both more efficient and more capable of handling the messy and continuous nature of the real world. The von Neumann bottleneck is a concept that describes the limit on throughput caused by the physical separation of the processing core and the memory bank. In our current systems, 61% of the total system energy is wasted just moving data back and forth between these two components. Think about that for a moment. Only 10% of the energy is actually spent on the actual math we care about. This is a fundamental physics wall. You cannot simply solve this by shrinking transistors further because the architecture scales power linearly with size. The bigger the model, the more energy we throw away into the void of the data bus. This slide shows the RAM memory bank connected to a GPU processing core by red arrows representing that massive energy drain. We are reaching a point where the cost of moving data outweighs the benefit of the calculation itself. To move forward, we must break this bottleneck and find a way to bring the math to the data instead of dragging the data to the math. This requires a total rethink of how we build chips. If we do not address this fundamental bottleneck, we will continue to hit a ceiling in performance and efficiency regardless of how advanced our manufacturing processes become. We are essentially fighting against the laws of thermodynamics in a losing battle. Let us look at the sheer scale of efficiency when we compare a human brain to our modern server racks. The human brain contains roughly 86 billion neurons and operates on a mere 20 watts of power. That is roughly the energy needed for a dim nightlight. Yet, it achieves the equivalent of 20 petaops of computational power. Now, look at the server stack on the right. To reach even a fraction of that complexity, we are burning through 70 kilowatts of power. These systems generate a massive thermal load that requires expensive cooling infrastructure and creates a huge environmental footprint. The contrast is staggering. We are comparing 20 watts to 70,000 watts. This disparity highlights why current AI development is hitting a wall. We are trying to brute force intelligence with electricity, while biology has found a way to create consciousness and complex spatial navigation with almost no energy at all. The brain achieves this through extreme optimization and sparse activity. Replicating this efficiency is the primary goal of neuromorphic engineering. We want to build systems that can think and act in the real world without needing a power plant attached to them. This represents a massive shift in our design philosophy, moving away from high power consumption toward biological levels of efficiency that could revolutionize portable and edge computing. Component number one of this new era is the Leaky integrate and fire neuron. We need to forget what we know about continuous floating point tensors and instead think in terms of discrete time. In this model, energy is only spent at the exact millisecond of a signal transfer. This accounts for a tiny amount of energy, roughly 10 to the power of negative 10 joules. The rest of the time, the system sits in silence. This leads to 99% temporal sparsity, meaning most of the system is inactive until it needs to be. As charge accumulates from incoming spikes, it builds up until it hits a threshold. If no new signal arrives, there is an exponential decay which we call the leak. This mimics the biological reality where neurons do not stay excited forever. By using this event-driven approach, we can slash energy consumption because we are no longer calculating zeros in a giant matrix. We only compute when there is an actual event to process. This temporal sparsity is one of the key secrets to biological efficiency. It allows the system to remain ready for action while consuming almost no power in its resting state. By adopting this model, we move toward a form of computing that is reactive and incredibly efficient, mirroring the spikes of activity seen in the human nervous system. Component number 2 focuses on the idea that the synapse is the memory. In traditional computing, we move data from the hard drive to the RAM and then to the CPU. In physical AI, data does not move. The computation happens exactly where the data lives. This eliminates the need for a memory bus entirely. This approach can lead to up to 28 quadrillion operations per second per watt. However, there is a catch known as hardware lock-in. Because the physical state of the material actually is the model, you cannot easily patch weights from a cloud server like you would with a software update. The weights are baked into the physical connections of the chip. This creates a highly efficient but also highly specialized piece of hardware. The red circle in the diagram shows where these intersections happen, creating a dense web of local processing. This is a radical departure from the general-purpose processors we use today, moving toward a model where hardware and software are one and the same. It means that to change the model, you might need to physically change the state of the chip. While this sounds restrictive, the performance gains are so massive that it justifies the trade-off. We are moving toward a world where the intelligence is embedded directly into the fabric of the machine itself, rather than being an abstract set of instructions. Moving on to component number 3, we look at the event-driven substrate. The most important thing to understand here is that there is no global clock. In a standard computer, every part of the chip ticks at the same frequency, wasting power even if nothing is happening. Here, we are computing at the speed of silence. This is an asynchronous operation where cores only switch or activate when a spike propagates through the network. This results in incredible power savings. For example, the True North chip draws less energy than a watch battery if no data hits it, totaling only 70 milliwatts. You can see the path of activity in the diagram, where only the red glowing squares are active, while the rest of the grid remains dark and dormant. This mirrors how our own brains work, as we do not use every neuron at every second. We only activate the specific circuits needed for a specific task, allowing for a massive scale of hardware to run on minimal power supplies. This lack of a global clock also reduces heat and interference, allowing for denser and more complex chips. It is a more natural way of processing information, where the data itself dictates when and where computation occurs. This asynchronous nature is fundamental to creating systems that can scale to billions of neurons without melting under their own heat generation. When we talk about scaling this technology, we look at projects like Intel's Hala Point. This system contains 1.15 billion neurons and over 140,000 neuromorphic cores. It offers 5 terabytes per second of inter-chip bandwidth and operates entirely without traditional memory buses. To put this in perspective, this system has the neural complexity of an owl's brain. An owl is capable of 3-dimensional spatial navigation and real-time tracking of prey in total darkness, all while running on just 2,600 watts. While that is more than a biological owl, it is a massive improvement over traditional supercomputers. The architecture is a dense cube of interconnected layers that allow for massive parallelism. We are finally reaching the point where we can build silicon systems that rival the structural complexity of small animals. This represents a major milestone in our journey to create physical AI that can interact with the real world in real time without being tethered to a massive power plant. Systems like Hala Point prove that we can scale these biological concepts to a level where they become useful for industrial and scientific applications. We are moving from small-scale experiments to full-scale neural systems that can handle the massive amounts of data required for modern robotics and complex environmental monitoring. Component number 4 is the silicon retina, also known as a dynamic vision sensor. Traditional cameras take dozens of full-frame pictures every second. Processing static, unchanged backgrounds in these frames wastes a massive amount of compute power. If you are filming a wall, A normal camera sends the same pixels over and over again, requiring the processor to check every single one. The silicon retina is different. It only outputs pixel location timestamps for changes in brightness. If nothing moves, nothing is sent. This creates a sparse and temporally native data feed. In the diagram, you see the X and Y axes with spikes along the time axis. These spikes represent only the movement or changes in the scene. This is how biological eyes work. Our brains are wired to detect motion and contrast rather than processing every static detail of our environment at all times. By using this event-based vision, we can reduce the data load by orders of magnitude, allowing for faster reaction times in robotics and autonomous systems. It also allows for much higher dynamic range, as the sensor can react to lighting changes in real time without getting blown out by overexposure. This is a perfect example of how copying biological sensors can lead to massive improvements in how machines perceive and interact with their surroundings. Learning in these systems follows a specific rule known as spike timing dependent plasticity, or STDP. Unlike traditional AI, where we freeze a model after training and ship it, these systems learn continuously, millisecond by millisecond. It is a local and real-time learning process. If neuron A predicts the firing of neuron B, the physical connection between them strengthens. This is the physical manifestation of learning through experience. However, STDP has its own challenges. It struggles with deep and complex networks when compared to global backpropagation used in standard deep learning. To get around this, researchers often have to use surrogate gradient workarounds to train these chips. You can see the red warning sign for surrogate gradients in the graphic, highlighting this current limitation. Despite these hurdles, the goal remains the same: to create a system that evolves and adapts to its environment through physical changes in its structure. We are moving away from static algorithms toward dynamic, living hardware that improves the more it is used in the real world. This continuous learning is essential for robots operating in unpredictable environments where they cannot rely on a pre-trained model. By allowing the hardware to learn on the fly, we create machines that are truly resilient and capable of adapting to new challenges as they arise. The ultimate output of this technology is the creation of sub-millisecond reflex loops. In traditional robotics, there is a significant computational lag between sensing an object and performing a movement. The data usually has to travel to a central processor or even a cloud server before a command is sent back. Physical AI erases this lag. By operating at biological timescales, we can create systems that react instantly without phoning home to a data center. The diagram shows a robotic arm with actuation tendons and motor controllers linked by a red reflex loop. This loop represents single millisecond latency. This level of speed is essential for tasks like catching a falling object or maintaining balance on uneven terrain. By bringing the intelligence directly into the limbs and sensors of the machine, we enable a level of fluidity and grace that was previously impossible. We are no longer building machines that think before they act. We are building machines that react as part of their physical nature. This has massive implications for prosthetics, manufacturing, and any field where split-second decisions are critical. Erasing the computational lag allows for a more seamless integration between the machine and the physical world, bringing us closer to a future where robots move with the natural agility of living creatures. Despite the promise of neuromorphic hardware, we must face the ecosystem reality and the system vulnerabilities. We are currently in a transition period where the software has not yet caught up to the hardware capabilities. While tools like Intel's Lava and PyNN exist, they currently lack the maturity and community support of industry standards like PyTorch or TensorFlow. Another major caveat is that converting artificial neural networks to spiking neural networks is a clumsy process. When we try to force legacy software onto neuromorphic hardware through a translation layer, we often lose the native temporal precision that makes these chips so special. The diagram shows this translation layer as a red block holding up a crumbling stack of traditional software. We need a fundamental shift in how we write code to fully realize the potential of these systems. We cannot simply port our old way of thinking into this new era. We need to develop native algorithms that are built from the ground up for event-driven, asynchronous computation. This software gap is currently the biggest hurdle to the widespread adoption of physical AI. Until we have a robust and user-friendly software stack, these amazing chips will remain locked in research labs. Building a bridge between traditional developers and neuromorphic hardware is the next great challenge for the industry. The transition to physical AI marks the end of the silicon era as we know it. We are beginning to realize that the last few decades were just an experiment in digital logic. The neuromorphic era is native to physics. This represents a philosophical boundary where we must ask at what point the functional replication of biological perception actually becomes biological. In this new era, a chip that learns is physically altered. As the text suggests, the hardware is the experience. We are seeing a move from the clean lines of logic gates to the tangled, organic complexity of a system that grows and adapts like a living organism. The diagram on this final slide shows this split beautifully, with rigid circuits on one side and growing neural structures on the other. This represents a total convergence of biology and engineering. We are no longer just building tools, we are building substrates for intelligence. This brings us to the end of this video. We hope you found it informative and engaging. If you have any questions or suggestions, please leave them in the comments below. Don't forget to like, share, and subscribe for more content like this. See you in the next video.